Our first speaker is Nathan Seiberg from the Institute for Advanced Study. And I have to say that Nadia is one of the few physicists that Steve was in awe of. And it's a great pleasure to have him here to speak at this conference. Take it away, Nadia.
Thank you. Can you hear me? Good. So I inaugurate the microphone and not only the center. It's really a pleasure to be here. And I thank the organizers for putting together this conference and for inviting me here. I also want to congratulate you on the new center. I have no doubt that it would be quite successful. I'm particularly honored to give this talk because Steve has been my hero, because his scientific breakthroughs have advanced science, of course, but they've also blazed the way, the path, for many young researchers, among them me. And his impeccable integrity made him a role model for many, again, including me. I've had many conversations with him about diverse topics, including, of course, physics, but also politics, world affairs, and others. And I've always been impressed by the breadth and depth of his knowledge and his logic, which always made the conclusion inevitable. So all of us will miss him dearly. The talk here has three parts, which can be seen in the title: quantum field theory, separation of scales and beyond. These are part 1, part 2, and part 3. Especially part 1 and 2 are topics that were very close to Steve's heart, and I'll recall his contributions. And part 3 is more modern, and I really wish Steve would have been around to help us figure it out. It would be more posing a problem than answering it. Now, we have a diverse audience here, people from different branches of physics and math, and even computer science. And so in order to put things in perspective, I'm going to give a broad brush introduction to physics in general, and then focusing on quantum field theory. So I've arranged that as a 2-by-2 matrix, where in the first row we have classical physics, and in the second row we have quantum physics. And in the 1-1 entry of the matrix, we have classical mechanics, which describes the time evolution of a finite number of particles. And I had to choose two people, so I chose Newton and Lagrange. And part of this discussion was a natural mathematical setting that came along with classical mechanics, and this is ordinary differential equations. This is extremely satisfying situation where there was new math, new physics, and they go hand in hand. Moving to the 19th century, we have classical field theory. This is the 1-2 entry of the matrix. We have the time evolution of an infinite number of degrees of freedom. For example, the electromagnetic field or the velocity field in the Navier-Stokes equations, and the metric. And I had to choose two names to put here. So these are Maxwell's and Einstein. And again, there's a natural mathematical setting that goes with it, which is PDE. So this is, again, very satisfying. New physics comes with new math, completely coherent. By today, it's well understood, although there are still many, many interesting questions that are still open, but it's more or less settled. Let's move to the second row of the matrix. This is quantum physics. And in the first column, we put time of the classical mechanics, which is time evolution of a finite number of quantum particles. This is a photo from the Solvay conference. Many of the people who were involved. The first thing we see is as we move from the 19th century to the 20th century is that there are many more physicists. And again, there is a very natural math that goes with it. Part of it is more rigorous than others. Part of it is the operators acting in a Hilbert space, well understood. And it's even important today, mostly in the context of quantum information and quantum computing. But more or less, the principles are understood. And now we go to the 2-2 entry of this matrix. And this is quantum field theory. And I basically, it's nice with PowerPoint. You can just copy the slide from before and make minor edits. It's a time evolution of an infinite number of quantum degrees of freedom. For example, the electromagnetic field. Now, here, there are many people who contributed, so I decided not to put any photo, although Weinberg should really be there at the top, and I will talk about him soon. But a lot is known, and there's still very exciting progress. But unlike the 3 other entries of the metrics, there is no natural mathematical setting. In fact, it's not yet mathematically rigorous, and some people use it to criticize the field. So I think this should be viewed as an opportunity. There's something very interesting in here, in this box, the thing that would be the counterpart of the other mathematical things. My personal view is that a new intellectual structure is needed. We'll refer to it as quantum field theory. And we'll see how this will be something for the future. Now, why are we interested in quantum field theory? The one-line summary is that quantum field theory is everywhere. And I'll start with some of the applications. I'll start with particle physics. This is the language which is used to describe the standard model of particle physics. And this is not characteristic. This is the best example of agreement between theory and experiment. This is the electron magnetic dipole moment. Theoretically, this is the number, and experimentally, this is the number. This is actually quite an amazing achievement of mankind. No other branch of science, let alone sociology and other branches of knowledge, gets even close to such agreement between theory and experiment. Also, when mathematicians and also some condensed matter physicists criticize continuum quantum field theory as not being rigorous, not well defined, I think this is a pure demonstration that we know what we are doing. This is not an accident. And every digit here taught us physics. Some of these digits here ended with a Nobel Prize, just for the digit. It was so deep. There's another lesson from that. I'm a theorist. You see, the experimentalists are ahead of us. So I think we should all work harder and find more digits. Maybe there would be a disagreement. And in fact, I think we might be on the verge of a disagreement for the counterpart of that for the muon, but I'm not an expert, so I will not go there. So this is quantum field theory for particle physics. The next topic is condensed matter physics. And it's really interesting that the progress and the understanding of quantum field theory went in parallel in condensed matter physics and in particle physics with a lot of cross-fertilization between these 2 distinct fields. They faced the same problems, and solutions were borrowed from one field to the other. I can go through a long list of that. But even though the problems are different and the math is very similar, what is going on here is that quantum field theory gives us good description of the long-distance behavior of matter. It describes different phases, like whether we have a conductor or not, whether the material is smooth or not, etc. And it also describes the phase transitions between different phases. And there is a very detailed quantitative description of these phases and the transitions between them. I'll say a little bit more about that later. The third topic, which was also close to Steve's heart, of course, the first one, he was one of the founders. The third was also something that was close to him, is cosmology, especially in the early universe, where quantum field theory plays a role in creating the fluctuations in the in the microwave background radiation coming from quantum fluctuations in the early universe. And of course, there are many others. This is a broad brush description of physics. Moving to the second half of the 20th century and the 21st century, we have string theory and quantum gravity. The string is a one-dimensional object. As it evolves in time, it sweeps a 2-dimensional world sheet, and we have a quantum field theory living on that world sheet. Also, there are limits of string theory. For example, when we go to very, very low energies, where Newton's constant is effectively 0, where the gravitational interactions are weak, and the remaining interactions are captured by quantum field theory. And in some cases, especially in gauge gravity duality that Eva described this morning, the whole theory is captured by quantum field theory. So there's a theme here. Wherever we look, the language we use to describe the physics is quantum field theory. And hence the title of this slide is Quantum Field Theory is Everywhere. And it's not only for physics, it's also useful in math. Over the last several decades, there have been many new developments in math, which were clearly stimulated by ideas in quantum field theory, which were, even if the quantum field theory itself was not rigorous, the mathematicians could then prove it in their own way and prove it and derive rigorous results. But the results were clearly motivated by physics. So the upshot of all that is that even though it's not well defined, we really know what we are doing. And the fact that it appears everywhere tells us that this is a very deep idea. It's clearly very deep. And it also has the other hallmark of a deep idea. It was designed to solve one problem, and then it solves other problems, which is always a sign that what we're doing is really deep. So my personal view is that there is a deep underlying structure that we do not yet fully understand, which encompasses all these developments. And therefore, I would like to refer to it as the language of physics. This is the language we describe physics everywhere. And if you don't know the subject, I can recommend a book. Take this book, it's 3 volumes. This is volume 1. And they're really fantastic. Now, I said the talk has 3 parts: quantum field theory, separation of scales, and beyond. This is my summary of quantum field theory and where it fits in the big picture of physics. So I'm moving to the second part. And again, I'll put it in a broader context. And this is the notion of separation of scales. In all of physics, but in fact, in all of science and most human knowledge, we have separation of scales in the sense that we have different descriptions at different length scales. And we can be experts in what happens at one length scale, knowing nothing what happens at much shorter length scales and what happens at much longer scales. We can focus on it one scale at a time. And in philosophy, this idea is known as reductionism, where the deep ideas are at shorter distances and follow from them the understanding at longer distances. So for example, when we study particle physics, we go deeper into matter, trying to peel the onion and find deeper and deeper truth at shorter and shorter distances that would give as the effect that eventually will give an understanding of what happens at longer distances. What most physicists do is not that, but they go in the opposite direction. They take known rules of physics, for example, Schrödinger equation, put some atoms in a box, and they try to use the known rules to find new phenomena. But both of them have this idea or this notion that we can study physics one length scale at a time. So let me give some examples. I was talking to a friend of mine who is a computer scientist, and he was surprised that people discuss entropy before they knew that this was the logarithm of number of states. Because originally people had thermodynamics and discussed all the notions of thermodynamics. There were no states. And eventually there was a deeper understanding in terms of states. So we can think of thermodynamics as the long distance effective description coming from the short distance statistical mechanics. The same thing is true in hydrodynamics. I've already mentioned the Navier-Stokes equations in the 19th century. These were PDEs that describe the flow of fluids. But what's really going on there, the deeper understanding, is that there are molecules there, lots of molecules, and they move around, and they bounce against each other, and it's very complicated. But most of this information is totally irrelevant in a very precise mathematical sense for describing the flow of the fluid. So the effective description of the fluid in hydrodynamics is very effective. And in fact, it was known before people knew that there are molecules around bouncing around. Recently, we saw the same thing in epidemiology when people became clearly more interested in the subject for obvious reasons. And you could study the virus and its RNA at short distances and maybe develop a vaccine or some medication. And then there's public policy at longer distances. Should you wear masks or not? What about 6 feet from each other? Maybe we should even block travel between countries. And you can participate in a discussion about whether we should close the border or not without keeping track of whether people wear masks or not. And you can discuss this separation between people or shelter in place and so forth without knowing anything about the structure of the virus. So at every length scale, you have a different description which is appropriate to that length scale. And of course, in quantum field theory, this idea of separation of scales is extremely important. And Weinberg was one of the people who pushed for it, and I'll soon come back to that. So overall, this shows us there is some simplification, and nature is kind to us, because it didn't have to work that way. It could have been that in order to figure out what's going on, we had to understand what happens at all length scales simultaneously, and then it would have been hopeless. So we are really fortunate that nature is kind to us, and we can study nature one scale at a time. In this context, I found a nice quote by Steve Weinberg that describes exactly that from 2021, a little bit before his death, where he says there is a school of philosophy of science associated in particular with the name of Thomas Kuhn that sees the development of science, particularly of physics, as a series of paradigm shifts in which our point of view changes so radically that we can barely understand the theories of earlier times. For example, quantum mechanics made classical mechanics obsolete because now we have the better rules and we can forget about the classical physics. And as we progress and we go deeper and deeper into the onion, find deeper and deeper truth, we can forget about the other knowledge, which was not precise enough. But then Steve continues and says, I don't believe it for a minute. I think our successful theories always survive as Newtonian mechanics has, and as I'm sure the standard model will survive as approximations. This is actually extremely deep. Yes, we have a deeper understanding at shorter distances. That's true, but we shouldn't forget the physics at longer distances. It's still very useful. And for most applications, we can work with classical physics, and we don't need to get into the intricacies of quantum mechanics. So this is really the point of the separation of scales, and you can see him smiling while he's saying that. This mine? So going back to quantum field theory, in this case, the idea of separation of scales is even more important because it translates into the renormalization group equation. And it's a very quantitative idea, goes usually primarily with Ken Wilson and Steve Weinberg, who pushed this idea of working things scale by scale and understanding the renormalization group that allows us to relate them. So what's the point here? We have different theories at short distances and long distances. I've already alluded to that, like the virus and its RNA at short distances, and whether we should keep distances at longer distances. And here, I would like to say more about that as follows. We formulate a theory at short distances, and I'll use interchangeably short distance and UV, which is ultraviolet, and IR, infrared, for the long distances. This is just a Fourier transform between them. And I couldn't use ultraviolet and infrared, so I put this color coding because otherwise you couldn't see anything. And this picture with the UV with an arrow to the IR is actually extremely helpful and extremely deep. And it has different views in different branches of physics. In condensed matter physics, we formulate the problem at short distances. Like we take some atoms, we put them in a box, we put some impurities, put some magnetic field, we shake it, and hope in the end we get a metal, or hope we get some superconductor or something. So we can think of this as being the question, and this is the answer. We formulate the problem here and would like to figure out what happens at longer distances. This is the answer. Traditionally in particle physics, the motion was in the opposite direction. We looked at some hadrons and we tried to figure out the shorter distance physics that leads to them, for example, quarks and gluons. But we have really a two-way street between the two of them. Even though the long distance physics follows from the short distance one, the research goes in the two directions. So now that we know that QCD is the theory of the strong force, people still use it, say on a computer, to try to calculate more accurately the spectrum of hadrons. So this is more in the spirit of the condensed matter approach, where we start at short distances and we go to the long distance theory. Now, let me say a few more words about that. We start with some material at short distances. We put some particles in a box and some atoms in a box and we shake it. And we could like to find the phase of the system at long distance. What's the long distance behavior? And interestingly, the answer to the question, which is down here, this answer is independent of most of the details at short distances. I mentioned that in the examples of the fluid. We have a differential equation for the flow of the fluid, and it is independent of most of the details of where the molecules run around. We don't have to keep track of every molecule of where it goes around. And technically, this is known as universality. And we have the description at long distances comes under the technical name effective description. It's effective because it's very efficient, and it's really effective. This is the way to solve the problem once you figure out what's going on there. And then you can get more details about that. And specifically, even if the short distance theory is on a lattice, as is often the case in condensed matter physics, the long distance physics is in the continuum. Just as at short distance, the hydrodynamics, we have molecules, it's very granular. At long distances, we have a smooth field of the velocity. And the same is true with materials, like this pointer is probably a lattice at short distances. But from the outside, it looks pretty smooth, and we can approximate it by the continuum. So let me say a little bit more word about that. So we can approximate space by a lattice. Notice my color coding, that this is this ultraviolet. For example, a cubic lattice. And then we put the degrees of freedom on the sites, the links, plaquettes, etc. Mathematicians use different names. They call the sites vertices and the links edges. I don't know why we cannot agree on universal terminology. And then we postulate some short distance interaction, some spins on every site, and the spins interact with each other. Maybe they are next to nearest neighbor interaction, etc. And typically, the low energy description is in terms of continuum quantum field theory. So the underlying lattice and its discreteness is gone, and at long distances, it looks completely smooth. So this is one of the reasons quantum field theory is so useful in condensed matter physics. Now, the lattice plays different roles in condensed matter and in high energy physics. In condensed matter physics, the lattice is physical. A lattice is formed, some crystal is formed by ions, and then there are electrons moving around, and we would like to figure out what the electrons do. And various phases of matter come from understanding how the electrons behave in this physical lattice. In high energy physics, we are in the continuum, but we still use the lattice. And we use the lattice either to define the theory, to give it a rigorous description of the theory, or, which is almost the same, in order to put it on the computer. Because we cannot put the continuum field theory on the computer, but we can put the lattice, the degrees of freedom on the lattice in the continuum. So this is the end of the second part of the talk. So first part was what's quantum field theory, why we are interested in it, why is it so successful, the fact that it's so successful and it's everywhere. The second part was the important thing of separation between ultraviolet and infrared, namely the fact that we have this separation of scales. But now I'm going to argue against it. There are very good reasons to believe that short distance and long distances can be mixed together. And this separation of scale that I've been talking about for so long now is special to these cases, but should not be the end of the story. So I'm going to give now a number of examples where UV and IR are mixed together, where the long distance and the short distance phenomena are mixed together, and long distance physics is extremely sensitive to short distance details, exactly the opposite of what I said earlier. So first of all, this is common in gravity. In gravity, short distances and long distances are mixed together, and there are several ways of seeing it. First, if you try to explore nature at short distances, you build an accelerator, and you throw particles at each other with higher and higher energy, and you try to focus the beam so that we have more and more collisions. And if you want to explore nature at shorter distances, you build a larger accelerator. You accelerate the particles even more so that you can learn what happens at shorter and shorter distances. That doesn't work with gravity. If you put more and more energy in order to explore nature at short distances, and you put it in a small volume so that there would be some collisions, the theory is smarter, says, stop, you cannot do that, because a black hole is formed and hides the short distance from you. So as you try to explore what happens at shorter and shorter distances, the theory stops you from doing it. And in fact, the more energy you pump in, the larger is the black hole. So again, we see suddenly that, wait a minute, it doesn't work the way it should have worked. It should have worked if we put more energy, we see what's going on at shorter and shorter distances. We have a better microscope, we explore better. No, with a better microscope, you explore worse. So that's what gravity does. Also, especially in the context of string theory, we have a lot of dualities where long distance and short distances are mixed together. We can't tell whether a string propagates on a long circle or a short circle. And in fact, many of the conceptual questions and confusions in quantum gravity, in one way or another, circle around this question. The information problem, the cosmological constant, and all that. Maybe that's not what's going on there, but at the moment, I can point that there is UVIR mixing in the context of gravity. Now, some of you might say, I'm not interested in gravity. I'm a traditional physicist doing standard things in the lab. Don't bother me with gravity. So now the next few examples would be examples without gravity. And first, examples that come from string theory. String theory is a consistent theory, and it has a parameter like Newton's constant, essentially playing the role of Newton's constant. And we can take a limit that would turn it off. So we turn a knob and make the coupling constant disappear, Newton's constant disappear. One way to do that is just go to very low energies, and then gravity decouples at low energies. I've already said it before. In that case, it's described by quantum field theory. But there are many other examples where we get more and more interest in quantum field theory. And in fact, many interesting developments, especially in connection with math over the last several decades, came from doing exactly that, finding field theories by turning off Newton's constant and learns new things about that field theory. However, that's not always the case. And there are two notable counterexamples, even within string theory. The first is something known little string theory. I'm not going to give any details. This is a known consistent story, consistent theory without gravity, in which long distances and short distances are mixed together. In this theory, there are no local operators. There is a good S matrix, but there is no local operator. And it also has this duality of mixing long and short distances. The second example is field theory on a non-commutative space. In quantum mechanics, the coordinate and momenta don't commute. So people can ask, can it be that the x direction and the y coordinates, the x coordinate and the y coordinates do not commute? So mathematicians have been interested in this. In fact, it happens even in physics. When you talk about physics of the first Landau level, the x direction and the y direction do not commute. They satisfy the Heisenberg algebra. Okay, so we have a space where the coordinates don't commute. This comes very naturally as a limit of string theory, so another reason to be interested in that. And the physics that happens there is that every particle is like a little dipole, and as you give it higher and higher momentum, you send it with higher and higher velocity, the dipole grows in the orthogonal direction. So as you try to explore short distances by sending the particle at higher and higher velocity, it gets bigger and bigger and has influence at longer and longer distances. There's nothing wrong with that. It's completely consistent, except that it violates this separation of the strict version of this separation of scales. There are also other aspects of this story that, comparing the theory on a commutative and a non-commutative space, the same theory, some ultraviolet divergences become infrared divergences. This is getting too technical, so I'm not going to say much about that. But again, you could say, these examples came from string theory. They were motivated by string theory. Maybe we shouldn't study them. So the last class of examples are the most conservative ones. And these are various exotic lattice models that were found over the last several decades, mostly by Ha and his followers. And in this case, they start with a lattice model, exactly the kind of model that I described earlier, with some spins on sites or links. And there's some nearest neighbor interaction. It does not look that exotic. It's an innocent looking model, except that it exhibits this UVIR mixing. And the long distance physics is extremely sensitive to short distance details. And there are some aspects of it. It has unusual symmetries, position dependent symmetries. So as the symmetry operator depends on where in space you run it. It also has excitations with restricted mobility, like particles that can be at the point and cannot move, or particles that can move along a line, but not along the orthogonal line, or can be in a plane, but not away from the plane. And the most interesting thing is that it has a very large ground state degeneracy. So we formulate the problem on a lattice with periodic boundary conditions, with Lx, Ly sites in Lz in the different directions. And the number of ground states is some function which is exponential of some function of the number of sites. Now, this is clearly UVIR mixing, because the number of ground states, which is clearly long distance physics, Clearly, infrared behavior is very sensitive to how many sites the lattice has. Just think of doing an approximation of an integral as a sum, and you add one more point, and all of a sudden your approximation is completely wrong. Something very funny happens here, and assuming that we have smooth functions in quantum field theory is not the case. In fact, this function here in the exponent typically grows linearly in the size, so it can get very macroscopic. It's not as extensive. It does not grow with the volume, only with the length of the system, but it's not monotonic. So we add another layer of sites, and the number of ground state drops to a number of 4 to 1. We add another layer, and it jumps again to be exponentially large. So I presented a number of examples against the UVIR dogma, and for all I know, there could be others. And I'm running out of time, so let me summarize the talk. We presented quantum field theory. We said it's everywhere, and it appears to be the language of physics. Various special things that we know, like classical mechanics, classical field theory, quantum mechanics, all of them are special cases of quantum field theory. And it also appears at the forefront of what people are interested in string theory, in condensed matter physics, and elsewhere. A property of quantum field theory is the separation of scales, which appears not only in physics, appears in all of science, and follows under this name of reductionism in philosophy, the deeper and deeper truth at shorter and shorter distances. And most of the details of the short distance theory are not important at long distances. And I said that we are fortunate that nature is so kind to us. However, and that's what I think is more interesting, is that in gravity, we have UVIR mixing. We said that with the example of the black hole, information problem, and others. And certain string theory constructions and various lattice models exhibit UVIR mixing without ever mentioning string theory. So what should we make of that? What does it all mean? Well, I wish Steve would have been around and I would ask him, because he thought a lot about separation of scales. A lot of these developments about separation of scales are due to him, especially in the context of effective theory of pions, which he was the first to write down, which was enormously important at the time. And this whole way of thinking is brought into question here. I don't know what to make of it, but I think this is if there are younger people in the audience, this is a good problem to figure out. So thank you for listening, and good luck for the center. I'm sure it will be successful.
Thank you, Nadi. We clearly have questions already.
Thanks for a great talk, first of all.
Thank you.
And second of all, there's something I don't understand about using the ground state degeneracy as a primary indication of importance. I could start with a state, or system rather, that has a ground state degeneracy of 10 to the 10th. And I could apply an infinitesimal perturbation that makes one of those 10 to the 10 states infinitesimally lower. I could never measure. Suddenly the ground state would become unique. So why do I know that it's important?
Yeah, so these systems are gapped. These systems are gapped. I failed to mention that, which means that under small deformations, there's a neighborhood in the coupling constant space, not just infinitesimal, there's a neighborhood in the coupling constant space that they remain, the ground state degeneracy is not lifted. That's actually one of the interests in these systems, is that I should say from the start, there is not a single material in the lab that realizes that, but there's no reason why there shouldn't be one. But if there is one, it has an enormous technological implication, because you can take one of these things, they are robust because of the gap that you asked about. There's a gap, so they are robust, and they have lots of states. So people think that this could be used for, say, for quantum memory. It's not like a qubit, which has two positions. This has 10 to the 20th position, and it's stable. Maybe it will be good for something.
Or maybe it's good that there aren't any such things, and separation of scales intuition actually works in the real world.
But we don't, even if it works for generic materials, there could be materials which are not generic, for which it's not true, and then it will be useful. Now you could say, maybe it's good that we don't have a quantum computer. Maybe it's good that AI does not yet rule us. Maybe, I don't want to get into this.
First, Daddy, I want to say that your talk was beautiful.
Thank you.
I think, however, you may have been a little too generous back around slides 9 or 10 for the ability of lattice gauge theory to calculate things. And I give you an example, and maybe I'll give you an example, maybe the example is obsolete. The example is in 1974, when I was a postdoc, and S.D. Eichner and I were postdocs at Cornell. Ken Wilson had us trying to calculate the electromagnetic form factor of the proton on the lattice. Fortunately, shortly after, well, as we struggled for a while, fortunately, the J psi was discovered. And I never worked on lattice gauge theory again. Esty did, but I don't think he ever calculated the electromagnetic form factor.
Well, I'd like to respond to that. I also worked a little bit on lattice gauge theory doing Monte Carlo in my youth, and I'm not doing it now, but there has been enormous progress in this field over the 3 years since the time you and I were postdocs until today. There's been enormous progress, and the numbers are really good today. The numbers are really good. There's still room for improvement. It's not perfect. There's still room for improvement, but the numbers are getting better. And I can imagine that with better computers, with better algorithms, it will get better.
So
I can hear you.
just keep talking, okay. There's another infrared IR connection, which is popularly known as the butterfly effect, the fact that initial conditions on a small scale can affect the system on a very large scale later. And I wonder if that has any connection to the ones.
Okay, this is an excellent question. My hunch is that the answer is no. But the fact that there is chaos, which is what you allude to, it exists. I'm not going to deny that. Chaos in quantum mechanics is less so than in classical physics, because roughly the quantum mechanical fluctuations kind of smear the initial conditions. Yet this UVIR mixing exists in bona fide quantum systems, so it has a different field. Now, I made many predictions about the evolution of physics in the past. Most of them turned out to be completely wrong. So maybe I'm also wrong about that one, but it feels a little bit different.
Question.
In the Fracton models that you described, are there any lessons to learn about like what the qualitative difference is between condensed matter systems that have UVIR mixing versus those that don't?
Yeah, that's a fantastic question. One of the shocking things there is that when you look at the model without analyzing it, you cannot tell the difference. They look essentially like the Ising model. Okay, the couplings are a little bit different, so it does not look that crazy, which is one of the reasons it is so interesting, because it looks like a garden variety model, but it exhibits this bizarre behavior. My sense is that this is a sign that there's something very important we are not understanding. These models are there. I remember personally, the first time I heard about that, I said, this cannot possibly be right. Somebody will debug it, and I don't want to waste my time. I was wrong. I think these models are there, and I think they're sending us a signal that our understanding is incomplete.
Excellent. So let's just thank Nadia again and go to our next one.